In this video, I want to demonstrate making an extended free body diagram for a seesaw. In order to make the extended free body diagram, you want to draw your beam not as a point, but as a distribution. I'll use a line here. I want to identify the pivot point P, which will be at the fulcrum, and it's also the center of mass of the beam. Now, there's going to be some forces acting on my beam. There is a 100 Newton force caused by the weight on the left. And then we have a 300 Newton force caused by the weight on the right. But is it possible that this system is actually in static equilibrium? Well, we'll do some calculations to find out whether it is or not. So we see that there's 1 meter between pivot point P and where the 100 Newton force is applied. We want to draw the R vector, which points from pivot point P to where the force is applied. And let's draw an R vector for the 300 Newton force as well. All right, at this point, in order to decide whether there will be a net torque on the system, we have to calculate the torques that are caused by each of these forces. So the torque due to the force on the left, it'll be that R vector times the magnitude of the force. And then we could also use the sine of the angle between them. That's part of the torque formula. So the torque of the 100 is going to be 1 meter, 100 newtons. And then we'll use sine of 90 because they are perpendicular. So we're actually going to get the maximum possible torque because those vectors are perpendicular. Okay, so that comes out to 100 Newton meters of torque. Now let's calculate the other torque. It's 3 times the weight, but it's also 1/3 the distance from the pivot point. So let's do a torque calculation for that. Notice that the 100 Newton weight would make our beam want to accelerate in a counterclockwise way about the pivot point P. But the 300 weight, it makes our beam want to accelerate clockwise. So I'm going to put a negative on torques that are clockwise. Okay, and we'll do the same calculation, but it's for the 300 weight now. So let's use 1/3 meter, 300 newtons, and then a sine of 90 because these are also perpendicular. I also have to make sure to put a negative on this one. So if you multiply that on calculator, you'll see it's negative 100 Newton meters. So what this shows is that the torques are actually equal and opposite in this problem. So what does that mean for our beam? Well, it means that it's not going to angularly accelerate. And it turns out that not only is the sum of the torques equal to 0, but the sum of the forces is equal to 0 as well. Because one thing that's not shown here is the force supplied by the fulcrum at the pivot point. That would be a normal force. In this case, we can actually calculate that normal force pretty easily. It has to balance with the other two forces. The pivot is responsible for holding up both the 100 and the 300 Newton forces. But it doesn't create any torque about pivot point P because it acts at pivot point P. It's no distance from pivot point P. So we verified here that the sum of the torques is 0, the sum of the forces is 0. So if our system starts off at rest, it's going to stay at rest. It's a condition called static equilibrium. On the problem below, try the same approach that I had done. See if that beam is in static equilibrium or not. If not, which way would it tend to want to angularly accelerate?